Greetings and welcome to multiple representations of constant velocity motion. In this video, what we're going to try to do here is to give you several different ways to represent constant velocity motion. We're going to use position time graphs, velocity time graphs, motion maps, words, and we're even going to show the actual motion using our little hiker guy here along the bottom. And so I'm trying to give you as many ways as possible to kind of link into constant velocity motion. Hopefully, if you can understand one representation, you'll be able to pick up on the other representations. So, here is a graph of position versus time. It represents a particular motion. You'll notice that I haven't actually used real numbers, especially on the position axis. And I'm going to call these seconds, right, whatever they are. They could be minutes, hours, whatever. But I'm just going to call them seconds to keep things simple. Now, the first thing I want to do here is to actually have our hiker guy walk the motion. You'll notice that the initial position, otherwise known as the y-intercept of a position time graph, is at 0. So our hiker guy will start at 0. Afterwards, he moves away from the origin, or in the positive direction, if you will, because he has a positive slope. And it's a constant slope, so he's going to move to the right constantly for 1, 2, 3, 4 seconds. And it's going to be a fairly slow velocity, because if you notice here, the slope is not very steep. Then for the next 1, 2 seconds, he's at rest, so he's going to stop. Notice no slope on the position time graph. And then for the last 2 seconds, he's going to move in a negative direction, which means he's going to move back towards 0, to the left, if you will. And he's going to go faster, right? Faster than he did here. How much faster? Well, take a look. If he moves this far on the way out, he's going to move the exact same distance on the way back because he's going back to 0. But he's doing it in only 2 seconds instead of 4 seconds. So same distance, half the time, he's going to have to move twice as fast. So watch his motion. Going to the right slowly for 4, stopping for 2, and then moving to the left twice as fast all the way back to 0. And watch it one more time here. Moving to the right slowly for 4 seconds, stopping for 2 seconds, and taking off to the left twice as fast and ending up back where he started. So the next step, let's do the velocity time graph. Again, remember that you see the velocity on a graph of position versus time by looking at the slope of a position time graph. That is, if you remember how we defined the velocity. So for the first 4 seconds, his velocity, slope, is positive and constant, but it's also pretty slow. So that would be represented here by a horizontal line on our velocity time graph because it's constant, above the time axis because it's positive, and near the time axis because it's slow. Then for the next 2 seconds, he stops, so that's back down on the time axis. Remember, anywhere on the time axis is 0 velocity, and we need to connect the two with the little dotted line because we have the discontinuity here, the sharp corner. Technically, you couldn't be moving and then not moving. You'd have to slow down, but we're trying to keep things simple. For the last 2 seconds, he moves with a negative constant velocity. So that's going to be below the time axis. How far below? Well, remember that just a moment ago, we decided that since he's moving the same distance in half the time, he'd have to be moving twice as fast. Therefore, his velocity should be twice as far below as it was above. The other way to analyze this velocity time graph is to remember that the area under the curve on a velocity time graph represents the displacement. And notice his displacement is the same size out as it is back. So the area here has to be the same size as the area here, which it certainly looks like on my graph. It's negative here because he's moving to the left and positive because he's moving to the right here, but it has to be the same size. Okay, our next step is to draw a motion map. And as I've done before, I'm going to put a dot for each second of time. So each hash mark on here is going to get its own dot. Well, at 0 time, he starts at 0 position. And 0 position is right above the end of the arrow. And by the way, you might want to read this. This is just telling you why this line is twice as far below as this is above. 1 second of time later, he's going to be moving to the right, and then he's going to move constantly to the right for 4 seconds. So there's 1 second, 2 seconds, 3 seconds, 4 seconds. Notice 1, 2, 3, 4 time intervals. Notice, too, that these dots are equidistant because the velocity is constant. Then a second later and 1 second later after that, he stopped, so we need to put dots up. Remember, this is a position reference line. So dots that are piled on top like this mean that you're stopping for 1, 2 seconds. Then he comes back to the left, but it only takes him 2 seconds to get all the way back to where he started. So he's got to get halfway back in 1 and all the way back in 2. Velocity arrows. Initially, the velocity arrows are short and point to the right because he's moving with a slow positive velocity. Then there's no velocity arrows because he's stopped for 2 seconds. And then his velocity arrows have to go to the left and be twice as long because he's moving twice as fast. So in words, the object starts at 0, then moves to the right or moves positive for 4 seconds, stops for 2 seconds, then moves to the left, or you could say moves in the negative direction, back to 0 at twice as fast of a speed in 2 seconds. There's lots of different ways to say this, but you have to get all the times and directions and all that in there. Now, here's the fun part. Let's see all of this motion together. So here's our little walker guy at 0, and you might want to rewind this a couple of times, and you can look at all the different graphs and the motion map all at once. So here's the motion. Moving to the right slowly for 4 seconds, stopping for 2 seconds, and then zipping back to where he started in 2 seconds, so twice as fast. One more time. Moving to the right slowly for 4 seconds, stopping for 2 seconds, and then zipping back to the left twice the velocity. Example number 2. This one's a little different because we're starting with a motion map as our given, and we're going to draw the corresponding position time graph and velocity time graph. But like we did before, the first thing we're going to do is, what is this actual motion that's represented by the by the motion map here? And the first thing we have to decide about this motion map is, where is the 0-second dot? Well, remember that you always start at the lowest level. So it's got to be one of these dots, because any stopping or changing, we're going to go up higher. So which of these dots is the first? Well, if we're moving to the left, because these arrows are pointing to the left, it must be this dot. So this must be the 0-second dot. Now notice that this 0-second dot is way to the right of 0 position. 0 position, always at the tail of the position reference line. So it's way to the right. So that means in our real life here, our hiker is going to start way to the right. And he's going to move slowly to the left for 4 units of time, 4 seconds, whatever it is. But then we get to an issue right here. Notice that we don't have 2 dots stacked up. It's not like this one over here. It's just 1 dot. Well, what does that mean when you only have 1 dot like that and we've jumped up a level? Well, consider what he's doing just before that dot and just after that dot. Just before that dot, he's moving to the left. Just after that dot, he's moving to the right. Since there's only 1 dot, basically what it means is he turns around instantly and moves to the right. So he's going to pivot and cut back to the right. You can't really do this. In real life, you'd have to slow down to the left and then speed back up to the right, but we're trying to keep things simple. So when you only have a single dot like this, you have to jump up the level so you don't overlap, and it means you're instantly changing direction, as opposed to over here where you're stopping because there's more than 1 dot. Then he moves to the right fast for 2 seconds. Notice it's faster because the dots are further apart and the arrows are longer, but he doesn't get back to where he started. And then he stops for 2 seconds. 3 dots is 2 intervals of time. So let's watch the motion. He's moving to the left. He instantly cuts back to the right. Goes back faster, and notice he ended to the left of where he started. Let's watch that one more time. Moving slowly to the left, pivoting to the right and moving faster, and then stopping to the left of where he started. So let's do the position time graph. Since the 0-second dot is way to the right in real life, then that is way above the time axis to start out. And then he goes to the left for 4 units of time, and notice he doesn't get all the way to 0. 0's way over here. Right? So that means a negative slope for the first 4 seconds, but not all the way down to the axis. Then he instantly changes direction. So what does that mean? Well, since on a position time graph, velocity is the slope, if he instantly changes from a negative velocity to a positive velocity, that means the slope has to instantly change from a negative slope to the positive slope. So we're going to get a sharp corner here. And he's going to go back to the right for 2 seconds, faster. So notice this slope is steeper than this slope, but he doesn't get all the way back to where he started. And then he stops for 2 seconds, which is a horizontal line. Velocity time graph. Well, he has a negative velocity for the first 4 seconds, which is pretty slow. So it's under the time axis because it's negative, but it's close to the time axis. Then he instantly changes direction and moves to the right faster. Notice here how this line is further above the time axis than this one, because he's going faster. But this area is not quite as big as this area because he doesn't get back to where he started. And even though we're not using numbers here, there's a lot we can really put into these graphs. And then he stops for 2 seconds. Again here, notice the positive velocity is faster than the original negative. So this is further away than this. But this area is smaller than this one because he doesn't actually get back to where he started. Okay, words. The object starts to the right of 0, moves to the left or negative for 4 seconds, then moves to the right or positive at a faster speed for 2 seconds, and stops for 2 seconds. So let's put this motion all together now. Moving slowly to the left for 4, not quite getting to 0, turning instantly around and moving faster, and then stopping for the last couple of seconds to the left of where he started. One more time. I'm just going to do this without talking. So here goes the motion. Feel free to rewind that if you want to see it again. So I hope you've learned something here from multiple representations of constant velocity motion.